Hello everyone. In this video we will cover center of gravity in centroids and we will talk about moment of inertia. So first let's talk about center of gravity in centroids. So we have here Cartesian system XYZ. We have this body. Now of course it's going to have a center of gravity somewhere uh, with like X bar, Y bar, Z bar. Now let's say we want to find the position of the centroid. Now, the way to do that, we need to do some integration here. So let's take a small particle here, dw, that's differential weight. We have x here, y, and z. Now, to get x bar, it's simply the integral of x dw over integral dw. Same for y bar. It's going to be integral of y dw over integral dw, and z bar is going to be integral z dw. Oh, this is integral, sorry. Now for anything else, volume is for volume, for example, we replace dw with dv. For distance, for whatever you want, it's going to be the same equation, you just change the notification on it. Now let's keep going with this. So here let's do maybe a small example. Let's say we have a body that's like this parabola over here. Okay, let's say the height over here is 1 meter, and this parabola has the equation x equals y squared. Now we need to do the integration. Now first let's get a chunk, anything dl, position x, y. Now dl is going to be the square root dx squared over dy squared. That's just from the Pythagorean theorem. So dx is going to equal the d of y squared. This is 2y. So we put that in here. We have 2y squared. And what's dy? dy is just 1. So we have plus 1 squared, which is 1 dy. Now to get x bar, we do the equation that we talked about before. So it's going to be the integral from 0 to 1, that's the length, x square root of 4y squared plus 1. Now I'm just expanding here, so 2y squared is 4y squared, which is here, plus 1 dy over integral 0 to 1 square root of 4y squared plus 1 dy. Now if we solve all this integral at the end, we're going to get 0.41. Now I'm not going to actually solve the integral here. They should be fairly simple. Those are covered in your calculus courses. Now we do the same thing for y bar, integral y dl over integral dl, and that's going to be over the length. So it's going to be integral 0 to 1 y square root 4y squared plus 1 blah blah blah. Now if you look at what's the difference between this and this, so here we have x, here we have y, and then we get a value of 0.574. Now all these, they're fairly simple, it's just basically just doing the equations. There's nothing special to it really. Now here let's say we have maybe a body. I'm gonna draw this Cartesian x, y, z. Let's say we have maybe distributed force 3D. Now we want to find the resultant force. So Fr is the integral of A over the distributed force dA. Now this is actually an equation which is the same thing of integral over volume d volume. Now for 3D it's just going to be the volume, and for 2D it's just going to be the area. Now if it's 2D like this, it's just the area for this. Now the same thing as before. If we want to get x bar, now notice how we just changed. So instead of dw we have p. Instead of dw we have p. pxy. It's the same thing over the integral area. Now this should be, this is actually the same as integrating integral over volume x dv over integral over volume dv. And to get y bar, we basically do this same equation. Instead of x, we have y. That's the only difference, and it's going to be the integral over the volume y dv over integral over the volume dv. Now, moving on. Now we'll just introduce and talk a little bit about moment of inertia. So, first of all, what is moment of inertia? So, like the definition, I guess, of moment of inertia is the mass property of a rigid body that determines the torque that is needed for a desired angular acceleration about an axis of rotation. So, let's say we have this rigid body that I drew over here. Let's take a chunk here, dA, position x, y, and the distance r here. Now the moment of inertia about the x-axis is simply the integral over the area y squared dA. Now these are basically just equation. The moment of inertia about the y-axis is integral a x squared dA, and the moment about this axis over here, which is the r, is integral over a r squared dA. Now this basically is ix plus iy. Well, because they're perpendicular. So now I'll talk about something very important that will be actually used a lot in all your future courses. Mechanics of solids, dynamics. You're gonna use this everywhere. So it's called the parallel axis theorem. Now, let's say I have the moment of inertia about x bar, any axis. Let's call it x bar here. How do I get moment of inertia about x? So this is just basically parallel axis theorem. It says it's going to be ix is ix bar plus the area times the distance, perpendicular distance squared. Now here I have the drawing of, just to, I guess, better represent it. Let's say we have the centroid here, C. We have dy here, dx, and d. And let's call this, this is x bar, and this is y bar. And x bar we have y prime and x prime. Now, so again, ix is ix parallel plus a dy squared. So ix about this axis, this is x. It's going to be the moment about here plus the area times dy squared. Now for iy is iy prime plus a dx squared. And JL is JC plus AD squared. Now this is D and this is DX. And this actually concludes, I guess, it gives a good introduction for what are centroids, what are moment of inertia. Now in this chapter it should be fairly simple problems. This is just basically to introduce you to future classes. You're going to be using those much more in the future, not really over here. And again, thank you everyone for listening.